Good afternoon, Professor.
Good afternoon, Caroline. Good afternoon. And good afternoon, Caitlin.
Good afternoon, Professor.
Good afternoon, Savannah. There, I saw
Good
the.
afternoon, Professor.
Oh, now you. Wait, is that? Oh, and there, of course, I lose the board. Okay, I totally saw Savannah's green square that time, and then I heard. Wait, was that? That wasn't Euban, was it? Who? Now there's a new. Well, okay, huh? And then I lost my. Was that Euban? Or it was Steven? Well, okay, anyway, I guess, okay. And and I lost the board, of course. Hang on one second. And we will get started. Oh no, wait a minute. This could be a bigger problem than usual. Oh, this is a true frozen. Hang on one second. I'm sorry. Something's actually frozen. Something's actually frozen. Ay, ay, ay. That's a new one. Ay, ay, ay. Oh, hold on. I'm sorry. Oh, okay. Okay, the board is reading. Okay, good afternoon, Caitlin. Good afternoon, Kevin. Good afternoon, Amanda. Good afternoon, Jose. Good afternoon, Mackenzie. Good afternoon, Samaya. Good afternoon, Estrella. Good afternoon, Rashman. Good afternoon, Adan. Good afternoon, Erica. Hi, Euban. Good afternoon, Stephen. One of you said hello. I know, but I don't know who. Okay, the board's coming back. So again, with deep apologies, increasing numbers of you have gotten your exam back, but many of you still have not. It still has no it's still a bummer. I apologize. They're happening, they're coming. But whether you got it back or not has nothing to do with anything other than probably an initial in your first name or something like that. So please don't infer anything if you haven't gotten it back, and don't worry. I mean, of course you're worried, but don't over worry. They're coming, I'm just worse than ever. No, that's not true. I'm just bad. But we're gonna just keep going, and all of this will be it's understood that it's not good. But we're gonna keep going with the material as soon as I get my board back. And also, okay. So we're just gonna get going with the material. Again, you have nothing new to me unless you have old things due to me. The final will be less stressful than the midterm, and we'll get to that soon. I know we have very little time left in the semester, but here, okay, I'm just trying to get the board, but we're going to go back to the material. Here we go. Okay, back to the material. What we're going to continue with right now is electrostatic fields. Oh no, don't tell me again. Oh, that's weird. Okay. Okay. We're going to go back to electrostatic fields. That's our big topic right now. We're trying to get to the second equation on the page. We have not said anything about that second equation yet, but the first equation on the page is what we've been working with. What we solved so last Wednesday, we solved a somewhat thick computational problem involving that first equation. Today, I want to stay on the topic of that first equation, but today I want to try to make things more conceptually or visually clear as to what it is that we're doing and what we're saying about these fields. I will say that the computational problem that we solved last Wednesday, a problem which usually does appear on the final exam, was about the sum of two vectors. We will go back and make allusions to that problem today, but it is true that one of you very kindly pointed out to me that night that I think I made a copy error doing the solution to that problem at one point. That is to say, we were doing a lot of computations, and one number, I think it seems that I mistranscribed from a diagram into the chart. And I'm very glad that one of you did catch that. That's terrific. And one of you pointed it out, which is doubly terrific. And that person should certainly submit for points in the appropriate portal. I don't think that I've gone back and corrected the notes yet. I will try to do that in the PDF that's uploaded to Google Classroom. So I don't think I've made the correction yet, but I do want to acknowledge that that was a very good observation. And I will make that correction in the PDF. But if you are looking over those notes, especially when you're studying, if you notice that one number just got changed from a finding to a chart, you're not crazy, you're right, and that was a mistake, and I need to correct it. So thank you again to the person who told me that. Okay, but what was that we were doing? What is going on with these electrostatic fields? Okay. What I want to do again is try to back up today and talk about what this means and try to give you more visualizations for what we mean when we talk about electrostatic field. So first of all, it's all coming from the equations right at the top of the page here. We are right now talking about the field vector that would exist at any and every point in space due to some point source of charge sitting at some location in space. The idea that we're saying right now is that if I put a point of charge somewhere in the world, that point of charge causes a field of information, in particular of vector information, to exist everywhere in the world. If I put a point of charge over here, then there are vectors everywhere over there and there and there, indicating what kind of force would be experienced if or when other points of charge were to find themselves at these points of space. Okay, let me say that again in a slightly different way. I'm saying that the electrostatic field is a function. It is a vector valued function. Like all functions, it has an input and it has an output. The input, hold on, I'm just going to change the view of the screen. And today, again, Wednesday was very computationally heavy. And the computation that we did on Wednesday, again, usually is one of the 2 or so problems that appears on the final exam. You do want to know ultimately how to do that computation. So again, I'm very glad that at least one person was following it so closely that she or he, even noticed where something went awry. Anyway, you do want to know that computation, but I don't expect it all to land or be immediately clear just because we did it once. Today, I want to sort of unpack the concepts behind that computation. So today, by the way, is a very good day to stop me at any time and put thoughts in the chat about what you think you maybe are or are not feeling comfortable with this field idea. Okay, it's all about the field idea today. So one way I'm trying to say what a field is to think of it as a vector valued function. The input of the field function is a point in space. You input any location in space, and what you get as output is a force that is waiting to act at that point in space. The input is place. The output is force waiting to happen. What do I mean by waiting to happen? A slightly more mathematically rigorous way to say waiting to happen is to say force per charge. So if we're talking quantitatively for a moment, if we're talking in units for a minute, well, some people are here. Sorry. When we're picturing the field function, what you input into the field function is a place. Specifically, okay, I'll be more clear. Specifically, a displacement from some agreed upon origin, some reference point like 0, 0 on a Cartesian graph. Oh, good afternoon. Good afternoon. Thank you for saying so. If we're talking about field, the field function, as in the equation written all the way up to the left, okay, it's a function. You put in R and what comes out is E. But notice you put in R is a vector, and what's going to come out is E is a vector. So let me break that. So it's a vector valued function. The input is some kind of vector. The output is some kind of vector. Let me break that down further. The input is a vector known as R with an arrow over it, sort of depicted down in the middle of this page here. The black R with an arrow over it is the input. What is R? That's the input that you put into the field function. What does it mean? R with an arrow over it is a displacement vector. It's a way of indicating location. Specifically, the R displacement vector is defined to point from some point source, some object, some proton or some electron or some huge number of protons jammed together into a tiny, tiny space, or some huge number of electrons jammed together into a tiny space. You have some point source, some amount of charge that's going to cause field, okay? It's located somewhere in space. It's called capital Q, written in blue here, in thick blue. So capital Q is some point source, some point of charge located somewhere in space. Then we fix our attention on some location, some point of interest, or what textbooks and websites often called some field point, some address, some location known as point P, the little brown thing in P in the diagram, okay? So we've got some source over here, some bunch of protons causing field over here, and we're fixing our attention. We're concerned about some location P over here. So first of all, the vector R is the displacement from Q to P. It's the vector whose length is the distance from Q to P, and whose direction is the direction that you would travel if you walked from Q to P, okay? So R is the displacement of our location of interest as measured from some point causing field. That's the input, vector R. The output is going to be a vector E, the red vector E that's sitting there, whose tail is at the brown point P. The output of this function is the field. Field is a vector, and you name the place, E names the vector. The vector has a direction and a magnitude. Okay, and what does the direction and the magnitude represent? They represent force per charge. Let me back up for a second. Just the input R is a displacement. It's measured in meters. Okay, it's how many meters some location is from some point source of charge. The input is measured in meters. The output field is a force per charge. It's measured in, or its magnitude is measured in newtons per coulomb. Newtons of force per coulomb of charge. Its magnitude is an indication or a computation, a measurement of how strongly each coulomb of positive charge that might be found at this location P. Sorry, let me say this sentence again. The newtons per coulomb, the magnitude of this E vector, is an indication of how intensely each coulomb of positive test charge would be pushed or pulled by Q, by capital Q, by the point source, how hard each coulomb of positive test charge would be pushed or pulled by the point source if each coulomb of test charge were to find itself at this location P. So it's how hard charges will be pushed or pulled if they're at location P due to the point source Q. And the direction of E is in what direction they would be pushed or pulled. Now, the sort of tricky thing about all this is that I keep saying, well, a tricky thing about all of this is that I keep saying that field is force per charge, that the units of field are newtons per coulomb. And I keep saying that the field is like a force waiting to happen, or how much force would be exerted on each charge that could be found at location P. It's all very sort of conditional and suppositional, and it sounds all very theoretical. This is what tends to confuse people about field. Like, why do I keep saying each bit of charge that would be found there? Why don't I just say each charge that is found there, right? I mean, that's one way you could put the question. Because there isn't necessary, because the whole idea of field is that it's all the information determining a force before the force even necessarily happens, or independent of whether the force ever actually happens. Let me back up again and remind you, a force is something one object does to another object. A force is an interaction between two objects. Always, a force is always that. Specifically, in the case of an electrostatic force, a force is something that the electrostatic force is the extent to which one point of charge pushes or pulls on another point of charge, just like the gravitational force is the extent to which one point of mass pulls on another point of mass. For there to be a force, there must be two objects interacting with each other, pushing or pulling on each other. That's what a force is. Field is, so force is what one object does to another object. Field is what one object does to a location in space. Field is what's happening even before the second object even comes along. If no second object ever comes along, so in this case, in the picture that we have on the page here, we have capital Q, blue letter capital Q, that stands for a point of charge that's sitting in space about to cause forces to happen. It's known as the source. It's there. It's going to cause things to happen. Things won't happen until there is some kind of second charge, what we like lowercase q, like lowercase q2, located somewhere in space to feel the force of charge one. There won't be a force until there's a second charge to feel the effects of the first charge. But what we say is, even before there's a force, even before a second charge comes along to experience this force, the information is still sitting there at space, waiting to affect and be incorporated by the second charge. That whether or not there's a second charge, there certainly is a first charge, the source charge, and it has a certain magnitude. And that is true, whether or not that magnitude is doing anything to anybody. And that first charge, that source charge, capital Q, is at a certain location. But whether or not anything else is in the universe, like accepting the impacts of that location. So what we say is, look, the description of this first charge, the information, its magnitude Q, and its distance and direction from any other given point P. All of that is known in the universe. It's still true that there is a Q and that there is an R, whether or not there's any other object there to experience all this. So all that information, the magnitude of the first Q and the displacement of that first Q from any point that we're looking at in space, all that information is there in a bundle that we call field. That all of that Q and that R together are making an arrow, a vector that's ready to act as a force the minute some second charge, called the test charge, comes along to that location to experience the vector. The vector is there, sitting ready to act on a second object. So the field is all of the relevant information, all the vital statistics, so to speak, of the source charge magnitude and the source charge location. All of that is bundled together into an arrow sitting at any and every location in space. And then when a second charge comes along to any location in space, it feels the effect of that arrow and experiences a force. In other words, we used to say proton exerts force on electron, but now instead we say proton creates field in space. If electron is in point in space, then field exerts force on electron in space. So we used to say proton exerts force on electron. Now we say proton creates field, field exerts force on electron. We think of there being an intermediary, a medium, so to speak, a repository or container of information that's mediating this force between the source charge and the test charge. And we think of that information as being there, whether or not the second charge is there to experience it. So what that information is measured in is newtons per coulomb, because it's the number of newtons that will be exerted on each coulomb that might be found at a given location. Bottom line to all this thing that I'm trying to say right now is, if you understand this right up here at the top, oops, sorry. So, oh no, there goes it. So why does that do that? Oh no, here we go. Okay. If you understand, no, there goes the board. Hold on 1 second. Okay, while the board refines itself. I know your board is still there. It's on a delay. It'll disappear. Then the other board will come back. What I'm trying to say is field is force per charge. Field is force per charge. Therefore, force is field times charge. Or put another, field is charge times force. Sometimes that's an easier way to look at it. I'm saying that if for example, and try to maybe write this down while the board is rediscovering itself. If the field at a certain location, okay, if the field at a certain location is 30 newtons per coulomb pointing north, then that means every coulomb of positive test charge that could be located at that place will experience a force of 30 newtons pointing due north. So if I put 1 coulomb of test charge at that spot, it would be pushed with 30 newtons of force to the due north. If I put a 2 coulomb test charge at that spot, each of the 2 coulombs would experience 30 newtons of force. So together, the 2 coulomb test charge would experience 60 coulombs of force. Like I'm saying, force equals charge times field. Field is how much force is happening per each coulomb that could be or would be there. But we say could be or would be because it doesn't matter whether the charge is actually there or not. The field is nonetheless there. The field is the force, is the magnitude and direction of force per each 1 coulomb of positive test charge that we could find at any location in space. I'm going to put the board back now. Erase something I didn't mean to erase. Okay. 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 Oh my God, again. Okay. Okay, this is I'll try to make this more concrete as we're going now. So force is something I do to you, it's measured in newtons. Field is something I do to space. It's measured in newtons per coulomb. Field is how much force I would exert on each coulomb of test charge. But what this diagram is also trying to point out, it's trying to really show what we mean when we say that this is a vector valued function. We're trying to show how a vector is the input and a separate vector is the output of this field function idea. So the input vector R is drawn in black here, and it points from capital Q, the point source, to point P, the location of interest, the location where we're trying to figure out what the field is due to the point source Q. So we picture this displacement vector R that points from Q to P. R as a vector has magnitude and direction. Its direction is designated by this R with a hat over it, R caret. The unit vector R is defined to be the entire R displacement vector divided by its own magnitude. So if the entire vector is 5 meters pointing northeast, then the unit vector for that is a vector that points in the northeast, but only has 1 unit length. It's the unit vector R hat is 5 meters pointing to the northeast divided by 5. That's the idea behind it. So it's 1 meter pointing to the northeast. The idea behind a unit vector is that it is a vector. It has direction. It has the direction of the original vector to which it corresponds, but it deliberately has divided out the magnitude. So the unit vector always points in a particular direction that we're trying to pay attention to, but it only has a size of 1, so that you can use it to express and track direction, but it doesn't affect the magnitudes of anything else. Similarly, the magnitude of R is just the letter R written without any symbols. That means how long the vector R is, but doesn't carry any information about its direction. So the whole idea behind this notation and everything is, we could say if you want to calculate the electrostatic field vector at the point P, right, you do it according to this equation all the way at the top left of the page here. To calculate the electric field vector E, right, you're going to be calculating a vector which is created from the vector R, but it's not the same vector as R. R is the input, E is the output. What do? You take the vector R, right? So what do? We take the information, the magnet. So I'm looking at the equation at the top left of this page, the equation that says E equals plus or minus this big constant times Q over R squared times R hat. Like it looks, I know to many of us, it looks like a very confusing equation. Just take it bit by bit. I'm saying that the E field at a point is a vector we construct the vector this way. First, we take all that information, we take the constant, we multiply it by the magnitude of the charge Q, and we divide by the square of R, just R, i.e. the square of just the distance, the magnitude of displacement between point charge Q and point location P, right? We bundle all that information together, the size of Q, the distance away that Q is, we put that all together with the constant, and that is one big magnitude. What do we do with that magnitude? We use that magnitude to scale up or scale down the vector R hat, R with a caret over it. R hat, right, is the small unit vector R that points from Q to P. So what we're really saying is, take a vector that just has size 1 that points from Q to P and then scale it up or scale it down by this magnitude that we just got, that the Q over R squared and everything, so that at the end of the day, we get a vector E whose size is determined by that information, the size of the original charge and the distance away of the original charge. The size of the E field vector is determined by all that, and the direction of the E field vector points directly along the line connecting Q to P, directly along that line. Like, notice, it's not a coincidence. R hat, the red little vector, and E vector, the red vector, they're both parallel to R. They were vectors constructed from the original displacement pointing from Q to P. So our final field vector is either directly along that line if Q was positive, if it was a proton, but if Q were negative, if we plugged in a negative value for Q, then our final E vector would have all the same magnitude and everything, but would be negative. It would point in the direction of negative R hat. That is to say, it would point back the other way, like along the same line, but anti-parallel. Meaning the E field vector, if it's produced by a positive point charge, it pushes out. And if it's produced by a negative point source, then the E field vector points in. If the original point source creating our field is positive, then it creates repulsion. It pushes out. If it's negative, it creates attraction. It pulls in. I say push out or pull in because what I'm always calculating, what I'm always talking about, what I'm always expressing with the E field vector is the force that would be exerted on each 1 coulomb of positive test charge that could be located at the point P. The source of this field could be positive or negative. But the idea of the field is that we're always discussing what would happen to a positive. The subject, so to speak, could be positive or negative, but the object, so to speak, is always positive. So since a positive would push another positive, whereas a negative would pull another positive, the vector symbols, I believe you'll find, make sense, that we always get a push out from positive Qs, and we get a pull in along R from negative Qs. Okay, I don't know if that helps anybody at all, right? But the bottom line, and I'm going to turn the page, the bottom line is that field is a vector valued function. You input a displacement R as you input a displacement R, indicating how far away you are from a certain charge of a certain size. And what we output is a force vector based on that information. And the force vector indicates how hard and in what direction every single coulomb of positive test charge would experience if found at that location. Force is what one charge does to another. It's measured in newtons. Field is what one charge does to space. It's measured in newtons per coulomb. Okay. But this whole diagram on this page here is what one charge would do to one location in space. What you were calculating Wednesday is what would happen to one location in space due to two charges that were nearby. What we did on Wednesday, and what one of you helped out with the correction, thank you again. What we did on Wednesday is we said, okay, what if there's like a source charge over here and there's a source charge of an opposite type of charge over here? What would be their combined effect or impact on some location over there at the origin of a coordinate system? And what we said is, well, each one, in effect, would deposit an E field vector at the origin. And so the total effect of the whole situation would be the sum of two vectors at that origin. And what we did, all of that computational work, was just to add two vectors, one the field contribution from one source charge, we added it to the field contribution vector from the other source charge. We added the two vectors together and got one final resulting vector that indicated what would happen to every 1 coulomb of positive test charge that might find itself at the origin. That's what we did. But I want to go, but that was very computational. What I want to do now is go in the other direction in my mind. I want to say, well, wait a second. What if we had one source, 1 point source of charge? We don't want to accidentally start thinking that one source, we don't want to start accidentally thinking that 1 point source of charge creates field only over here at this one location of interest, P. Like, we focused all of our attention on Wednesday on the origin, the point 0,0, just because we did, because we were caring about what would be the vector that lands there at the origin due to these other two charges. The whole idea is we just picked that location because we wanted to. The whole idea is that once you put charges in the universe, charges create field vectors everywhere. That the field is a vector valued function, meaning you put a charge over here, for every point in space you name, there is a vector sitting at that point in space ready to go. So this picture right here is trying to show you, like, if I put one proton, one positive point source in the middle of my coordinate system, in the middle of the lab, in the middle of space, then I can draw a representative array of vectors spreading out from this charge. And what they represent is, they're representative. I mean, they're in principle, really, there's, for every point in space you imagine, there's a vector sitting there. But wherever vectors you're picturing would all follow the pattern of these arrows. What is this pattern? Well, number one, notice that all the arrows point along radial lines directly away from the point source. Meaning, no matter where you might find some bit of test charge, it will be forced along the line R that connects plus Q to it. And it'll be specifically pushed out along that line because the point source in this case is positive. It pushes on other positives. So all the vectors in space, and this picture supposedly goes on forever, no matter what location you picture, there's a little arrow there pointing away from the original charge, and an arrow that has a certain size that represents the number of newtons per coulomb waiting to exert at that location. Notice that the arrows get smaller and smaller as we get farther and farther from the point source. That's the idea of R squared being in the denominator. The farther away you are, R squared, the smaller the overall force per charge is occurring. So this is a representation of, the idea is you pick the location, there's an arrow sitting there that tells you how hard and in what direction each 1 coulomb of charge would be pushed due to this source. If, however, I had a negative source, it's the same picture, the same vector field diagram, only now all the arrows are pointing in, like I indicated before, because we're always picturing, when we talk about field, we're always picturing what would happen or what will happen to a positive receiver, to a positive, what we call test charge. So positives would push on positives, but negatives would pull on positives, right? So this is the vector field diagram due to a negative source, okay? I'm going to pause for a second. I know that this was, we're going to start making this more concrete in a moment. And the way I don't want to make it concrete with numbers today. I want to make it concrete with more pictures. We're going to be talking a lot about pictures today. The goal of today is to try and help you get better and better at picturing what I mean when I say field. Field is an abstract notion. I know that. If you don't feel like you totally get what I mean by field yet, fine and good. If you felt like you totally, fully, 100% understood what I meant by field, I would find that slightly suspicious and slightly concerning. Your goal right now is not to 100% feel complete comfort with what I'm saying about field. Your goal is to feel like you're getting a slightly more and more and more confident picture of it as we proceed. And I mean that honestly to everybody. Like it's not a complicated notion, but it is a hard and abstract notion, this notion of fields. I'm trying to capture what they mean by many different modes, partly mathematical, partly verbal, partly pictures. Okay, I want you guys to stay with me, and I'm going to pause for a second. What we're right now trying to picture is the field, how to picture or imagine what it means to think about the field produced by one point of charge. I'm going to go further with this in a moment, but I want to pause for a second. Please give me your electronic hand if you sort of feel like you're sort of with me so far. Like if you're like on a scale from 1 to 5, thank you, Stephen. Okay. Thank you. Okay. Thank you, man. Okay, cool. That's fast. All right. That's good. I won't even give the scale then. If you're great. I see many of you. Okay, great. Then I'm going to keep going. And I was going to say on a scale from 1 to 5, if you felt like 3 or above or something, but I'll accept it. Okay, great. Because here's what I'm going to do now. This is what we're depicting or picturing is the field due to a point charge. And again, if I had a choice right now, if anybody says field to me right now, if someone says the field due to a proton, what I would picture is a whole bunch of arrows everywhere in space, right? And a bunch of arrows pointing out from the proton. Like that's what I'm trying to say. And each arrow means that if I looked at that point in space, that's how hard and what direction I'd be pushed. Okay. Now, again, of course you all understand. I'm not literally saying that there's literally arrows in space. I mean, this is abstract enough. I don't want you to think I'm crazy. Well, not for that reason. But what I am saying, I'm not saying that there's literal like styrofoam arrows sitting in space, but what I am saying that there's information sitting in space. That is what I am saying. And that's like the hard part about this. I am saying that the minute you put a proton somewhere in the universe, then everywhere else in the universe, at every other point in the universe, somehow there's this little bundle of data, so to speak, of information, specifically the vital stats of that proton that we just put into space. Like I am saying that. I'm saying if you put a proton right here, then somehow over here in space, the size of that proton and the location of that proton are like over here in space. Now, I don't know like exactly really how. I'm picturing it as an arrow. Because that seems to be the most effective, straightforward, that seems to be the best method human beings have come up with so far for us to picture this information and to calculate with this information and make predictions based on this information. I'm saying that if there's a proton over here, then over here in this point of space, there's an arrow ready to go. There's like a push waiting to happen in that way and with a certain size, the size being determined by the size of the proton and the location of the proton. I'm saying that the proton, the minute it comes into being, it deposits its vital stats everywhere in the world. And then when electrons come to any point in the world, they feel those vital stats as a force. Now, again, when I put it that way, I don't know if that makes it more clear. To some of you, that might have just made it more clear. You might be thinking, oh, okay, yeah, I can sort of, okay, if that's what he's saying, sure. Some of you might be saying, well, I got it a minute ago when it was about vectors, but now, like what? He's saying there's like information everywhere in space just because there's like a proton in space? And I'm saying, yeah, that is what I'm saying. Like, and I bet you, if you just heard me and if you have any difficulty with what I'm saying, I want to tell you this. If you have any difficulty with the fact that I'm saying that there's information everywhere in space, the moment that there's a proton somewhere in space, if you have difficulty with that, good, because honestly, that probably means you don't like what I'm saying. It probably means you find something sort of uncomfortable or disagreeable about what I'm saying, which means you do understand it. Okay, honestly, if you don't like the idea of information sitting in space, that's because you are hearing my words and you are hearing what I'm saying and you are understanding those words and you're like, that does not really seem possible or realistic or scientific to me. Yes, it wouldn't seem possible or realistic or scientific to me either. It seems very weird to believe that because there's a proton over here, there's information describing that proton over here. That is very weird. If you think it's weird, you are getting what I'm saying. But please remember why I'm saying it. Why we believe that is because we know from experience that if you put a proton over here, and then you put an electron over here, the electron over here gets pulled toward the proton without touching it, without the proton touching it, right? Remember, this is all originally from an observation or set of reproducible, testable, precise observations about what we call action at a distance. We believe in this field thing, or we use this field idea because what we do apparently know to be true is this very, very surprising phenomenon that when you put a proton over here and then you put an electron over here, the electron will get pulled to the proton, number one, without touching it at all, and number two, it'll get pulled to the proton at a rate, like with a number of newtons, that seems to be very precisely, measurably determined by exactly how big that proton is and how far away that proton is, to the point where when the electron starts coming closer and closer, we can measure and see that the force is actually changing. The force pulling on it is getting bigger and bigger. In other words, I'm not saying that this is expected. I'm not saying I would have thought the world would work this way, not at all. But I'm saying, apparently, we're scientists. We're not philosophers. I mean, we might also be philosophers, but we're scientists. What we're saying is it looks like the world does work this way. It looks like protons over here pull on electrons over here with an amount and in a direction that seems precisely determined by exactly how big the electron is and how far away it is. And if you change the size of the electron or you bring it to a different location, apparently the proton adjusts its force accordingly, without touching. So apparently the information of what's going on over here in space is somehow over there in space at all times. That idea, I'm not saying it's a happy idea. Well, it's actually a very exciting idea, but I'm not saying it's an expected idea. I'm not saying, of course, why wouldn't you believe this? Like, why wouldn't you have thought of this? No, I'm saying, can you believe this? Apparently this is what happens. And it happens with gravity in the same exact way. Put a mass over here and a mass over here gets pulled toward it in an amount that is fully determined by how big each mass is and how far apart they are. So what we say when it comes to these forces that happen at a distance, these forces that happen fundamentally through space, since they seem to require and entail information exchange through space, we say that the information is contained in or transmitted through this thing called a field. We don't really know what a field is any more than you do. Please don't miss it. Like, I'm not saying, of course, therefore fields. We all get them, obviously, and they're all green and they smell like yak. Like, no, like I don't know exactly what a field is. I picture it as a bunch of arrows because it's the best, most useful picture I can come up with, but I don't know exactly what it is. I just know that it's the word field is the word for the idea that the information describing what's going on at this point in space over here seems to be accessible to each and every point in space over here. That's what the field is. And to this point right now, we're picturing the field as this forest of arrows. Now, that's a lot of arrows to draw. And it's a lot of arrows to picture for just one point. I mean, I'm saying right here, this would be just a representative array of arrows that we would picture due to just one electron sitting in the middle of the lab. That's a lot to draw. There's got to be well, it turns out there is a simpler, smoother, more appropriate way to sort of tie these arrows up in our mind and picture something that's a little bit less cumbersome. So we move from the vector field idea, which is not wrong. It's not wrong, and it'll never leave us as scientists. But we actually, in the modern day, we do something a little bit more slick. From the vector field diagrams, what this says is we build a newer, more convenient picture or model of what's happening with fields called a field line diagram, okay? You can picture fields, and I still do to this day, often, depending on the context, someone says, oh, there's a field over here due to that problem. I'll picture a whole bunch of arrows in space, okay? But sometimes that's a lot to picture, and it's not that easy to do calculations with. So instead, often what I'll do, what 19th century, 20th century, 21st century physicists do is instead of picturing a vector field, we picture this thing called a field line diagram. In a field line diagram, all the vectors get connected together. So in the case Now, so in the case of a point source, at first the picture doesn't seem that different. Here's the picture of a field line diagram from a point source. So if I have a proton like in the middle of the lab or the middle of the outer space sitting there, it creates a field of arrows that radiate out just like before. But the one difference now is I connect up all those arrows that were getting smaller and smaller and smaller in the other picture, they're all connected up. So instead of like 3 arrows per slot, I have like 1 big arrow per slot. That doesn't seem like a major difference yet, perhaps, but it becomes a very significant difference once we start looking at the fields due to anything more complicated than just 1 point. And that is ultimately our goal, is to look at the field due to things more complicated than just 1 point. So here's the field line diagram due to a positive point source. And in this case, the arrows, the lines radiate out forever, just like before, but here they don't get shorter and shorter, okay? So similarly, if I were doing the field line diagram from a negative point source, it would look like this. Same idea, just everything pointing in, just like before, okay? And this doesn't seem like a major distinction yet, but it is a distinction. I was drawing vectors before, now I was drawing field vectors, now I'm drawing field lines. They are still arrows, but they're not vectors anymore. Why do I say they're not vectors anymore? Because while they still do have direction, they don't have magnitude in the same way as before. In the field line diagram, the direction of force per charge that is indicated at any point in space is still represented by the orientation, by the tip-tail alignment of the lines. So if a line has an arrow pointing out, then that means if you found yourself somewhere on that line, yes, you as a positive test charge, you'd be pushed out. Like direction still is read the same way with tips and tails. But now there's no length of arrows to be read anymore. All the arrows are connected up. Arrows are not shorter than other arrows in particular. And the typical arrow will go on forever. It'll have an infinite length. So we can't read magnitude anymore from arrow length. What we say now is that the density of lines per area on the page now indicates strength of field. What do I mean by that? I mean, look at this picture. If this is or this picture, if this is the field, if this is supposed to represent the field due to a positive point source, then what you notice is that right near the point source, like I'm trying not to draw this, but like, not that it's such a great picture, but in here, the lines are really close to one another. They're really dense. There's a high number of lines per unit area on the page. Whereas out here, the lines are really spread out. Furthermore, the way they're spread out here, they're all spread out in the same way. Like if you pick a certain distance, R, then all the lines are spread out by that same amount at R. In here, they're all much more crowded, but they're crowded by this, to the same extent if I pick the same radius. So the strength of the field, the intensity of the force per unit charge that you would experience at a point in space is indicated in this picture by how crowded the lines are. The greater the number of lines per unit area on the page, the greater the magnitude of field that exists at the point in space represented by that page. I'll say that again. The greater number of lines per unit area on the page, the greater amount of field strength in the region of space depicted by that page. Okay, so density of lines now indicates magnitude of field. Okay, how does this work, or what does this do for us? Well, again, all of this would be a little bit overkill if all we ever looked at was the field due to 1 point of charge. But what we're actually trying to do here is look at the fields created by more complicated, more realistic configurations. Like last Wednesday, you were calculating the field at the origin due to 2 points of charge. each of them created their own field line picture. And so each of them deposited their own set of vectors at every point in space. So you picked a point in space and you said, well, there's a vector coming from one point of charge, of one source point, and there's a different vector coming from the other source. You added the two vectors together and you said, aha, here's what the field is over at this location, right? But you did all of that mathematical work. We did all that computational work just to get what the field was doing at one particular location due to two sources. What if we had wanted to draw a picture of what was happening everywhere in space due to the sum of those two point sources? Or what if we want to draw everything in all of space due to anything even more complicated than just two? In other words, each one of these pictures that I've drawn you so far really is kind of telling you what the field in space would be like due to the nucleus of a hydrogen atom. What if we want to depict the effect of an entire hydrogen atom, a proton and an electron, or quark forbid, like a helium atom, like two protons, two electrons? Like what if we wanted to get at all realistic and talk about molecules or anything? Like, what do fields start looking like then? Well, I'm glad you asked. We have 19 minutes. That is perfect. I'm going to switch. So this is the end of the notes that I'm giving you for today. These will, of course, be uploaded into the PDF, into the Google Classroom. And I'll correct again. Thank you again, person whose initials might or might not be things that I will say right now. I will correct the computational error in the old PDF at some point. But now I'm going to do a switch screens. I want to show you something you could just do yourself if you just typed into Google. Whoa, hello, you don't want to see that person's recommendation, do you? No, oh God, wait, you definitely don't. I mean, no, it's okay if you, but wait, this is the wrong. Okay, here we go. Oh, you definitely want to see that. Okay. Here's what I want to show you. You could just find this by just typing in EFieldLines or EFieldLineDiagrams into Google Images. I don't know why it's taking so long to load. Here we go, I think. Wait. Okay, yes. Okay, well, actually, go back. Okay, again, there's nothing particularly, I mean, this happens to be phys-libretext.org. You can find a whole bunch of stuff like this on Google Images. What I'm showing you first right now on your screen. Oh, God, your screen is totally paused. You really are looking at this person's recommendation. Why is it? Hold on. And it doesn't matter. You don't know him. It's not a John J person. Don't even worry about it. Hold on. Let me just put the... Hold on. I'm just putting you thing back. All right, let's try this again. Okay. What I have right here is, first of all, just a slightly more precise, more accurate rendering of what I was saying a few minutes ago. This right now would be like the vector field diagram due to one positive point source located at the origin of a three-dimensional Cartesian coordinate system. So just like I was saying before, this is not supposed to be new information, it's just a better picture. If you put like a proton at the origin of a coordinate system, then every point in space that you imagine anywhere in space, you would, due to that one proton, you'd find a little arrow pointing out from that proton. And the farther away you get from that proton, the smaller the arrows are, because the arrows, the vectors, represent force per charge, the number of newtons that would be exerted on each coulomb of test charge that you could find at any location. Again, I keep saying newtons per coulomb, and I keep saying the test charge that you could find at a location, because I'm trying to say that the force per charge, the field, is there in space, whether or not you find a second charge there. I'm not saying we don't find a second charge there, and I'm not saying we do, and I'm not saying that we're trying to predict the chances that we do. I'm just saying that the idea of the field is that it is the information sitting there at space, ready to go. The information, so each arrow that's there at space is really telling that point in space, okay, there's a proton at the origin, it's this big, like, just so you know, we're ready to exert 14 newtons of force on each 1 coulomb of charge that might be found here. If there is a coulomb of charge found here, we're going to exert 14 newtons of force. If 2 coulombs are found here, we're going to exert a force of 28 newtons, et cetera, right? So that's what this picture says. But you see, it's a lot of arrows to draw, especially once you're in 3 dimensions. So instead, we go to the picture on the left of, there's 2 diagrams in red on your screen, I believe. The one to the left is just what I just drew on my board. It's the field line diagram due to 1 positive point source. But now, if you move over to the right, this is where things get a little bit more interesting, a lot more interesting. And now we've got 15 minutes. I know this has all been very abstract and maybe boring. If you're going to listen to anything, I would definitely try to listen to the next 15 minutes with me. Like, even if you've been taking a mental break, like, reconfigure now, please. Because I think it'll be more concrete now that you're looking at this picture. But I also think I'm going to say some things that are very specific. And, you know, if you can get them the first time, it'll save you a lot of heartache. So here's the first thing I'm saying about this picture to the right. The more complicated red. Well, all right, no, I'm going to stop just because this is that important. I know we have 14 minutes. Can you just raise your electronic hand if you're still with me? Like, if you see the picture to the right and you know that's what I'm. Thank you. Awesome. That was fast. I love this class. Did I mention? Awesome. I really do. Thank you. You really deserve much better treatment than you get from me. Okay. Okay. So cool. So you're all looking at that picture. So here's the first thing about that picture. That is a picture of the electrostatic field lines, the field created by or due to a dipole, a pair of equal and opposite source charges. Okay, I know you get that. I mean, I believe you get that. Let me be more specific. So in a way, this is very much like the larger all space rendering of what we were trying to do on last Wednesday. Remember, last Wednesday, we had a positive charge over here, and we had a different negative charge over there. Now, granted, on Wednesday, they happened to be of different sizes. Like, one was +3 and one was one was like +5 and the other was -3 or something. So they weren't exactly equal. Okay, that's true. But so this picture would look a little different. But just please understand, for starters, that what we did on Wednesday is we looked at the effect of these 2 opposite points on Wednesday. We had 2 opposite point charges, and we figured out their combined effect on 1 point in space over here at the origin. We took the vector from one of them that pointed at the origin and the vector from the other that landed at the origin, and we added those 2 vectors together, and we got the resulting vector at the origin. In other words, we got the combined effect of those 2 point sources on one particular location in space known as the origin. That's also what this diagram is showing. This diagram is showing the combined effect of 2 charges, what they together are doing to points in space, the force per charge that they're creating, waiting to happen at points in space. Only the difference in this picture is it's showing for tons and tons of points in space. It's showing the pattern for all points in space. It's not just focusing on one particular point in space. So we got a vector, this at a point in space due to 2 sources. This one is taking all the vectors that would be deposited everywhere, all the resulting vectors. Like, if you went to every single point in space, added the 2 vectors together, got a vector for that point in space, and then went to another point in space, got a new vector, and stitched them all together, you get a picture like this. So first of all, just note, we spent all period last Wednesday just adding 2 vectors to get 1 vector at one location. Can you imagine how long that would take, or how much work we'd have to do if we had to look at all the vectors everywhere? This is meant to combine into one picture all of that work for all of space due to just 2 point sources. Okay, that's number one. So this could be just a bunch of vectors drawn everywhere, but that would be even a lot more to draw. So we tie together all the vectors and make it slightly simpler to look at, slightly smoother to look at. But the other point, did I just lose? Okay. But the other point, maybe that one, I don't know what I just said. Maybe that was obvious. I don't, but here's the part that's really not obvious, or it wasn't to me as a student. Just like last Wednesday, we were looking at the combined effect of the two charges on space. Same thing here. This diagram is not meant to show you what the positive is doing to the negative. I'm going to say it one more time because it's people unconsciously always think that it is. I mean, they don't even know that they think that, but it's very easy to make a mistake and misread this diagram. What I want to say again is this diagram is not telling you what the positive is doing to the negative or what the negative is doing to the positive. It's not trying to tell you that positives and negatives attract each other, even though it sort of looks like it is. It's not trying to tell you how positive and negative would pull together. It's imagine that the positive and negative are stuck in the lab, like we nailed them down on a lab table, or we nailed this high, or they're in a hydrogen atom, so they're fixed, relative to each other, sort of. Like where the positive and the negative are nailed down, and all these red curvy lines are meant to indicate what combined impact they have on space. These lines are meant to tell you what would happen if you found one positive Coulomb of test charge located at any given point in space depicted by this picture. So, for example, we have 9 minutes left. For example, can you see my, yes, you can. Okay. Say you go to this point, right along the horizontal line and equidistant between the positive and negative. Okay. Say you look right here. What that arrow, what that red line is trying to tell you is two things. One is it's saying, okay, if there were a third, positive, if there were a third, like Coulomb of positive test charge located at that dot right here, then first of all, it would be pushed to the right. It'd be pushed to the right partly because the left dark blue positive thing would be repelling it to the right, but also it would be pulled to the right because the light blue negative would, on its right, would be pulling it, right? It'd be pushed by the dark blue and it'd be pulled by the light blue, and both of those arrows would agree with each other. They're both going in the same direction. So so in effect, if you found yourself at that point equidistant between the two, there would be a vector right there from one and another vector from the other, and they'd both be in total agreement with each other. They'd both be long vectors pointing to the right, so we would add them together like we did on Wednesday, and we get one super long arrow pointing to the right. So if you were right here, you'd get shoved very much to the right. And that's why if you went up a little bit or down a little bit, you find that the field lines are very crowded together. They're very dense here because wherever you find yourself in this region, you not only would be pushed toward the negative, but you as a third party, right? Again, I'm not talking about what would happen to the sources. I'm talking about what the sources are doing to some test charge that might be there. Any test charge that was in this region would be shoved very intensely to the right because, like, say if I go up here, say if I go right here, where the line starts curving a little bit, right? It starts curving a little bit. Like, what's going on with that? Well, like up here, if I just look at the vector that is being contributed by the positive, the dark blue positive on my left, the dark blue positive on the left is pushing up and to the right to a location right here. So I get one vector that points up and to the right. From the light blue, I get a vector that's pointing down and to the right, like we did yesterday. Like we did last Wednesday, right? If you pick this location right here, we get a vector that's up and to the right and another vector that's down and to the right. So we would add those vectors together. And if we were dead in the middle, horizontally between the two, then the up of the dark blue, the up component of the vector would cancel out with the down component from the light blue. The up and down would cancel out. We'd be left with just rightward pointing components. So we would be shoved to the right, even if we were over here, right? But you see, like if we were a little bit like over here, if we were a little bit like or here, then the upward component of push due to the dark blue would be bigger than the downward component of pull from the light blue because I'm closer to the dark blue over here. You see what I'm saying? Like the dark blue would have a bigger effect than the light blue over here. So the up component would be bigger than the down component. So the net resulting vector over here would point more up than down, and it would end up shoving me somewhat up and to the right. I'm saying, in other words, wherever you go, you look at any, bit of red line, the tangent to that line is itself a vector that is the vector sum of the two vectors that were produced by the original sources. Like anywhere you go on any one of these red lines is a vector, the likes of which we computed last Wednesday, but we're just showing them all up here. So finally, if you end up going like to up here in this region or something, yeah, ups are canceling with downs, and we're left with just rights. But you see the rightward component of a push up here is a lot weaker, smaller than the rightward components of vectors down here because we're so much farther away up here. And the magnitudes of all these vectors is always based on 1 over r squared, right? Where r is the distance, not from positive to negative, but from each charge to wherever you are, to the point of interest, right? So up here, r is really big. So the field magnitudes are really small. So these lines are very spread out, very undense. But here, the forces are very strong. The lines are very dense. So the way we read field line diagrams, again, is the direction of a field line indicates the direction of the net force per charge. But the density of the field lines indicates the magnitude of field. Strong magnitude here, weak magnitude there. If we were to look at two charges, now look at this. If you were to look at this picture in the middle, picture B, okay, very similar thing, 2-point charges creating field lines. But in this picture B, they're both positive. So they're both pushing out. So if you went anywhere in this region right here, you see the lines are super undense. The lines and here are really, they're barely, they're not crowded at all because you'd find very weak field here. Because if you were right dead center between those two charges, the left charge would push you to the right, but the right charge would push you to the left. So the net effect would be 0. You wouldn't go anywhere, right? And if you go up to, you see what I'm saying, hopefully. The bottom line of what I'm saying is that, and then one more thing, I guess, if you go to this complicated thing, look, say now this, we're still dealing with situations that are comparatively simple. Like, what is this? This is a positive source over here and a negative source over here, but these charges are not the same magnitude. In fact, it even asks this to ask you to consider whether this plus or this minus seems to have a greater charge magnitude. And if you look at the picture, you can tell once you get used to this, that it's the plus that has a much stronger magnitude than the minus. It's, in fact, if you read up above the picture, it says there's about 3 times as many lines leaving this plus as there are lines entering the minus. Therefore, the positive charge is, we're inferring that the positive charge is 3 times as strong as the negative charge. So the picture starts to become unbalanced and less symmetric than the other pictures. The whole idea behind a field line picture is field lines absolutely can be curved. They're not vectors. They can be curved. Furthermore, they go on forever unless they start at a positive and land on a negative. We'll talk more about that on Wednesday. Field lines are not the same as vectors. Field lines are built up from vectors, but we read them differently. The density of field lines indicates the magnitude of field, and the pattern of the field lines indicates the pattern of the charge distribution. I think it is 4. It's 4. Okay, we're going to do more with this, but So from here on in, when we're picturing fields, we tend to picture field lines. It's 4:20. I'm going to cut it at that. Again, you're being very indulgent and patient with me. You don't owe me anything more until the end, unless you do owe me something old, just like I owe you some old things. But just keep on keeping on with me, and I'll hang around for a minute if there's any questions. Other than that, I will see you Wednesday. I'll see you Wednesday.
Have a good day, Professor.
Thank you.
Bye, Chris. Thank you.
Thank you very much. Thank you. I'm gonna change it. I'll hang out for a second if there's questions, and I'll. Okay, yes, have a great day. Thank you. Okay.